we know that we have to compete with what the existing market is. And so it's not enough for us just to be green. We have to be able to compete on price. So we have to make sure that any products we make are at least as cost effective as the existing materials, but preferably and actually ideally what we push towards is to actually have our products be more cost effective. In fact, the two major products on biochemicals that we've spent most of our time focused on, we chose those explicitly because the current manufacturing costs and therefore the current sales prices are very, very high, and that restricts their uptake in the marketplace. So we actually focused on these products with the idea of using biology to drive the cost down significantly. First of those is a molecule called glucaric acid. This is something that's very useful in a number of areas, and our particular focus has been on being able to produce it for the materials market. And so we're focused on so-called hyperbranched polymers, and those are materials that would have very favorable properties like superabsorbency. And so you can think about it in terms of using less material, which is often very beneficial, to get the same function in terms of its ability to be able to absorb water. The other molecule we've spent a significant time focusing on is something called 3-hydroxy-gamma-butyrolactone, and this is actually an intermediate in pharmaceutical manufacturing. It's used in the production of a number of statins, which are the cholesterol-lowering drugs, and more recently has been associated with a broad class of new antibiotics. And so as we know with pharmaceuticals, anytime we can bring the cost of manufacturing down for those, that has a positive outcome in terms of being able to generate cost savings. So in that case, we are specifically looking at a very high value compound whose current cost is really unaffordable for very cheap manufacturing. And so our objective in that case is to be able to significantly bring the costs down by using a novel biological route that we've developed rather than relying on traditional chemical synthesis routes. There's another area where we're just really beginning to explore, and that's to have an integration of the strain engineering and the process engineering. One of the things that we know is that as we think about going from bench scale science, so what happens in our laboratory, towards manufacturing, where you have a large facility that has exhaust pipes and lots of different stainless steel reactors, there's an integration that has to happen between how you engineer a strain and how you actually bring this process to market. And so we're really excited about new research that's really just beginning for us in collaboration with other colleagues about how we integrate those processes and try to select certain microbes, and that is the biological systems, to be able to integrate better with new kinds of bioprocessing technologies. Most chemical processes are actually continuous. What that means is that you start the plant will run for many, many weeks, usually for about a year, 50 weeks out of the year, before it has to be stopped and then modified for preventive maintenance, any repairs done, and then the process continues to run. By comparison, most biological processes, the vast majority, are so-called batch processes or fed batch processes, where they may run for several days to at most a couple of weeks at a time. And as engineers, we can do the calculations that show that continuous processing can be much more efficient economically and have much higher productivity than batch processing. But there are some very specific limitations that make it difficult to do this with biology. One of these being contamination. What we're hoping that we can use these new processing approaches and processing technologies to actually make an environment that's naturally sterile in the sense that it's specific for the kinds of microbes that we're interested in. So this allows us to do the kind of engineering we've always done, to do it in a different microbe, to allow us now to have access to this richer way of products that we know that we can engineer microbes to make, but to think about pairing that naturally with a bioprocessing system that will really take us to the point where we can achieve the economies of scale and the manufacturing robustness that we would need for commercialization.